It's day 23 of the advent of compiler optimizations. Today we're going to look at how the switch statement can be optimized by compilers. Let's start by writing a simple routine that switches a value and returns a different value. So unsigned design, decide even, unsigned x, switch x, case 1, return 100, case 2, return 200, case 3. You can see the pattern forming here, case 4, return 400, case 5, return, you guessed it, 500, otherwise let's return 0. What does the compiler generate for us here? Now, this is pretty clever. We're using Clang, and Clang has worked out that the entire function only returns 100 times whatever we gave it in x, as long as x is less than 5. And it has done what you might imagine. It is actually unconditionally multiplying by 100. Then it's doing some comparisons and then conditionally moving either 0 or the value times 100 into the result register, EAX. That's pretty neat. Let's see what GCC does. I'm intrigued now. GCC does the same too, so both compilers are able to do the same thing. Although, interestingly, GCC is using a MOV EAX, 0 instead of a XOR EAX, EAX. That's pretty unusual. Or maybe, the XOR? Yeah, no, I don't know why it's doing that. A mystery. It's funny, during the filming of this series, I found a number of compiler oddities that I've filed as bugs. If you read the blog posts that are linked in the description, then you'll see some of the interesting side quests that I've been on while I've been preparing these videos and blog posts. Anyway, let's look at something a bit more interesting. I'm going to go back to Clang, if I can. Clang 21.1, x86, there we are. What if there were not such an obvious pattern in the values that we're returning? So let's just try. We'll use the same dense set of values on the left hand side, that is 1 2 3 4 5, and then we'll just make up some numbers here. We'll return 1, we'll return 5284, we'll 2511, we'll return 483, 9999. So now we've just got a random set of numbers. The compiler still hasn't generated the switch jump table that I was kind of expecting it to. Instead, it has turned this whole thing into a lookup table and indexes it by the x value. So here we decrement EDI, set x to 0. If EDI is above 4, so it already decremented it by 1 to account for the fact that the lookup table will be indexed 0 based. So now the valid range is 0 through 4. So if it's above 4, then either it subtracted 1 and went all the way round up to a massive number, or it was above that value anyway. Then we go to AoCO, which returns with the 0 value that we've still got in EAX. Otherwise, we just look up a value inside this table here, one and the various random numbers I picked up. And then it looks like Compiler Explorer's had a bit of a moment and hasn't filtered out some of the debug symbols. So there's a bug for me to file later on. Either way, we've got pretty efficient code. And you can imagine this would generalize to a lot of other things that would happen. Let's try something else. So at the moment, we've got a dense set of input values, and so the compiler could use a table. But as soon as we spread those values out too much, then we know that the compiler can't use a table anymore, because the table will either be huge or just not feasible to create. So what if we have, instead, let's just switch these around the other way. So 1 can be 1, 5284 can be 2, 2511 can be 3, 483 can be 4, and then so now the return values are what was this one? It doesn't matter which one it is, I know, but it's kind of like I want to be consistently random. Now, interestingly, the compiler has generated a bunch of comparisons, but it hasn't just checked them one after another. We should see that the compiler is sort of doing a binary search. Let's see what it is actually doing here with those numbers are made up. So the first thing it's doing is comparing it with 2510. Interesting. If it's less than or equal to 2510, then we know it must either be 1 or 483, or else it's a value that needs to return 0. So we're going to go to a place that's only going to check those numbers. Otherwise, we know it's either 2511 or 5284 or 9999. And so that is in fact what we see it comparing. And then if it's not, presumably this LBBO10, if we go down to the bottom, yeah, that's the thing that returns 0. So there's the 5284 being 2, there's the 9999 being, let's go down to 909, being a 3. So yeah, we can see that it's done the work here. Let's just, for completion's sake, let's check the other side. So here, this is the branch which is the values less than or equal to 2510. So we've only got 1 and 483, and then it handles those appropriately. So it's kind of turned our switch into a binary search. Maybe not the most efficient one. I'm surprised that it doesn't just compare with 2511 and then it gets two answers. It either knows it's exactly 2511, in which case it could jump if equal, and then it could jump if less than to the thing that handles this. But by and large, it's done a reasonable job here. Let's have a quick look at what GCC would do. x86, and GCC does compare with 2511. Jump if equal to, yes, this is return 3. Otherwise, if it's bigger. Below. I always get confused at those. If it's below, it goes to L11, and then it does the check with only the values that are less than 2511. Otherwise, it does the other checks here, which is interesting. And on here, that's interesting. I've just realized it's doing some kind of clever trick for checking if it's either 0 or if it's 999, it's going to do set EAL and then multiply it by 5. Okay. Well, that's interesting. I'm not quite sure why it decided to do that, but it's a way of getting 0 or 5, I suppose. Fun things there. Compilers have lots of tricks up their sleeve, and it's really interesting to see how they shake out. Another way that I've spotted compilers using switch statements in clever ways. Obviously, here I'm just returning directly, which is not quite the same as most switch statements. Most of the time, you'll see that they'll make a jump table and jump to different areas of the code. But a classic that you might have seen is, please don't write this yourself. But you could say, hey, is this a space? And I can say switch C case space case new line case tab case R, and what's the other one? V, I think. Return true, otherwise return false. False. So this, is a poor man's, is this a space or not? And what we can see here is that GCC takes the input value, subtracts 9 from it. 9 happens to be the lowest value of all these ASCII values of space and tab and whatever. 9 is in fact tab. So we subtract 9 from it. Now we've got a value that's either negative, i.e. or very, very, very high, because it's wrapped around, or it's between the values 0 and I guess, what is it? Space is 32. 32 minus 9. 32 minus 9 is 23, I think. Either way, we've got a value that if it's in the range of the things that we care about, it'll be between 0 and 23. Then we're looking at this strange number here. And this strange number, if you look at the hex version of it, the hex version gives you a bit more of a clue. It actually has 1 bit set for whether this is a space or not. Effectively, it's taken the lookup table that would have been built of, true being the values for space, new line, tab, return, and vertical space, and it's bit packed it into a single register, into a single value that it can move into a register. Then it does a bit test. This bit test says, is the eth bit set in racks? If so, it sets the carry flag. Now, bit test unfortunately wraps around. If the value that it's testing is greater than the width of the register, which is 64 bits, then it kind of wraps around. So that means we also have to range check to see whether or not the EDI was in the range of 0 to 23, which it does here by comparing with 24 and then conditionally moving if not below 24. And this is after we've subtracted 9. So if it's not in the range of valid values, then we're going to move EDX over the EAX. So EAX will be 0 or 1, depending on whether that bit was set in the magic bit pattern that we've got there. But if it was outside of bounds, it might have been erroneously set. So we write over the bit value with a 0 if it was outside of the bounds. And so we get a very efficient, is this a space or not? That doesn't support Unicode, and you should definitely use stud is space and not my version here. Just while we're here, let's quickly see how Clang handles this. It's always fun to look at Clang x86. And Clang has a slightly different way of doing this. It's comparing ahead of time, is this above 33? If so, then CL is set. So that would mean that set, if it's below 33, then CL will be 1, otherwise CL will be 0. So we're already checking to see if the character was inside the valid range. Then we're checking a 32-bit pattern here, which has, you can see it's got bit 32 set there. If you look in the hex version here, the 0x1 is bit 32, and then 0000 and then 2E00 is presumably the bit pattern of new line and tab and whatever. And 32 is a space, that's why that's important. And then it shifts the value down by the right number of bits, which means it pulls down the ith bit, the cth bit, into bit 0, and then it ands it with the CL register. So what we get is the lowest bit is the bit that would be the lookup table, the cth bit of the lookup table, and then we and it with a value that is 1 if we're in range and 0 if we're out of range. So fascinating stuff. We're getting near the end now of the Advent, and it's quite sad. I've got so many more things I'd love to talk to you about, but there's only one more real day. I look forward to seeing you tomorrow for the last one in this series.